Hello, good evening everyone. Am I audible to you?
Yes.
Yes, yes, yes.
Okay, thank you. So today we are going to start week 4 discussion for the Solar Photovoltaics Principal Technology and Material course, which is being taken by Professor Ashish Garg from IIT Kanpur. And I am Ravi Kumar, a PMRF research scholar presently at IIT Bombay. So before starting this lecture, I just want to know, are you following the lectures? Have you
Yes,
completed all 20 lectures? Yes, no, maybe, or some?
yes.
Okay. You can write in the chat box as well. If you are not comfortable in the speaking, then you can write in the chat box. And I want this class to be more interactive so that we can learn more. So this is week 4 assignment, week 4 discussion, assignment discussion. Only some lectures are okay. If you are done only few, then it's fine. I'll just tell you, go and do all the lectures and follow the course. It will be beneficial for you. So from the first class until the third lecture, like third assignment discussion, we have seen what is semiconductor, we have seen intrinsic semiconductor, we have seen p-type semiconductor, n-type semiconductor, and we have seen the diffusion or like carrier transport. Okay, so now we have seen this semiconductor one by one p-type and one n-type. So today what we are going to do, we are going to see PN semiconductor or PN junction semiconductor. What is this, how it is formed, we will just study in this lecture, or we will just understand it. So before starting this, I just want to know what is your thinking about this. If we have a p-type semiconductor and then we have a n-type semiconductor, so how we are making PN junction? I just take an example. Let's see. Just let me know if it is true or not. I see if this is a PN kind of semiconductor and this is N kind of semiconductor. So do we join it like this? Or if we just join them with the conductor wire, will it be a PN junction? So when it will be a PN junction? Connecting wire, sir. Okay. So according to you, if we have a p type, we have n type semiconductor, and we just join them with a wire or just any conducting material, then it will be a pn type semiconductor. What others say? Is it really true? Have you studied somewhere how a p-n junction is formed, like this manufacturing of this p-n junction diode or solar cell?
No, sir. How about now?
No. Okay. So I'll tell you, this is not like if we are having p type and n type and we are just connecting them, it won't be create a p-n junction. So what we need to do, we need to deposit things. 1 minute. Wait a minute. Sorry. उधर भी क्लास सब Yeah, I'm sorry for the disturbance. So this is not like this. If we are having a p type semiconductor or n type semiconductor, we are connecting with the wires, it won't be create a p-n junction. So for this, what we do, we take, so for this, what we do generally, we take a p-type material or p-type semiconductor, and then we deposit on this. Deposition is take place like vapor deposition. This p-type, if this is n-type semiconductor, then we will just keep it in the p-type environment, and this p-type will be coming on the n-type atom by atom. So this connection is at atomic level, but connecting wires won't create a connection at atomic level. So this is the way how a p-n junction is being created. So, okay. So do you know the band gap of p-type semiconductor? Do you know the band gap of n-type semiconductor? And most of you already know the band gap of p-n-type semiconductor. So I'll just draw once. So this is for what? Like it is conduction valence band, conduction band, valence band, conduction band. Which one is p type? Which one is, I am writing A and B. Which one is p type and which one is n type?
A is P type and B is N type.
Okay, A is p type and it is n type. So for the p-n junction, what it is Fermi level? I'll just write F. So for the p-n junction, those Fermi levels should be at same level. So then and this band will be bending. So this bending is due to what factor? It is conduction band.
Electric field.
Yes, electric field. So this is the band diagram of p-n junction. Second thing is formation of depletion region. How this depletion region formation take place. So this bending area is our depletion region. So we will see how it is forming in a PN junction diode. And also the width of this depletion region as well. In the next slide I'll show you. So this is a P and N type semiconductor. We are making them PN junction diode. So what is happening? It is diffusion is taking place. Why it is diffusion here? It is showing diffusion like this. Why? What is the force behind this diffusion? Why diffusion take place?
Concentration gradient.
Yes. Difference in concentration or concentration gradient. So if we say these are electrons and these electrons are going towards P type, why? Because the concentration here is more. And due to this diffusion, what happens? A depletion region formation take place after some balancing between these diffusions. And in the depletion region, we don't have any free charge carrier. Here you can see neither hole or neither electron. Now let's talk about the width of this depletion region. On what factor does it depends? This formation is depending on what? Concentration difference. And concentration depends on what? Concentration. From where these, in the N type semiconductor, from where these electrons are coming. For the N type, what is the source of electron? Doping.
Yes.
Increasing concentration, and concentration affecting depletion region. So we can say depletion region width will be depend on doping. Okay. So this is the same image. We can say this is P type, N type, and this concentration, actually the width is inversely proportional to the doping. We have a formula. I'll show you in the next slide as well. So here you can see the width here is less as compared to this one. So from here we can say here P is highly doped. P is highly doped. And this is the graph showing electric field. This is the graph showing electric field variation inside this depletion region. And sorry, it is the charge. P type is these positive are the positive charges, these negative are negative charges. And this is the electric field variation. And this is the our potential difference variation. Yes. So this is the formula about which I am talking about. So this is the width of depletion region and it depends on concentration. We can say depletion region is inversely proportional to the doping concentration. So width inversely proportional to the doping. Fine. Okay, let's move. So there are two types of carrier moment and we have seen in the previous lecture as well. So I just want you to name them. What are the ways a carrier move inside a semiconductor? carrier moment in equilibrium. Leave it this equilibrium. Just tell me the name of carrier moment mechanism.
Deep and diffusion.
Sorry, my voice is clear to you?
Yes, sir.
Because I am seeing some lagging in my video, so I am just confirming from you if it is fine. If it is not, then I can change my internet connection. Just let me know.
Yeah.
Fine?
Fine, sir.
Okay. So there are two types of carrier movement, diffusion and drift. You already know diffusion and drift. So just revision. Diffusion is because of concentration difference
Carrier concentration.
and drift is because of
Electric field.
electric field. So just let me know if a semiconductor, if a PN junction semiconductor or PN junction diode, we can say diode, it is at equilibrium. So which phenomena will take place, diffusion or drift?
Sir, can you repeat it?
If a semiconductor or PN junction diode is at equilibrium condition, equilibrium means we are not having any kind of biasing, no forward bias, no backward bias. So what carrier moment will take place? Just remember the previous picture I shown.
Sir,
Both
diffusion. Diffusion.
diffusion. Yes, diffusion. And what about the electric field? Do we have any electric field in equilibrium condition? Yes.
Yes, sir. At the depletion medium, they both are cancelled.
Yes. Then drift will also take place. So here we can see this is a picture of PN junction, and here in the P type we have hole or electron concentration. What kind of carrier concentration is more? Give me answers. What kind of carrier concentration is more in P type? It is clearly visible
Sir,
here.
holes.
Holes.
Hole.
In N type it is electron.
Yes.
So diffusion of holes will go in this direction. It is visible here. Same diffusion of electron will go this direction. Now electric field direction is from positive to negative or negative to positive?
Negative. Minus to plus.
Minus to plus.
Yes.
Minus to plus. Electric field direction.
Plus to minus. Positive to negative.
Positive to negative. Here also
Yes.
we can see
Correct.
this is the direction of electric field. So if I am putting an electron here, it is positive to negative. And just see if I am putting an electron here in between. So where it will go?
Right.
Positive side.
Yes.
Yes.
No, sorry, sir. Yes.
Electron is negatively charged. Electric field is,
Electron will go to the hole.
yes. No, I'm not asking about hole and electron. I'm just asking if we have an electron here and electric field direction is this, and we have positive charge this side and negative charge this side. So where it will move?
Sir, towards
towards
P type,
how
P
it
side.
will, why?
Sir, electric field from positive to negative, na, your
See,
electron.
electric field is not here. Electric field is enclosed in this box. So
Okay.
just forget about this concentration and even this concentration. Just focus on this. This side is positive charge and this side is negative charge. And an electron is here in middle, in between. So where it will go?
It will go towards positive charge.
Yes, it will go towards positive charge. So this is the direction of electron. This is a drifting, and this is the, and hole will be go opposite in the negative side. So this is the direction of holes. So it is a carrier moment in the equilibrium. So any one of you have seen these animations in the PV education ORG?
Yes, sir.
Other than Mala Day, other students know about this PV education? Yes, no? You can write in the chat box. It's okay if you know, and if you don't know, that's equally fine. There is nothing to worry. I'll take you to this website very soon. Just wait. So let's move to the next part, which is the biasing of PN junction. Now tell me how many ways we can bias a PN junction.
Towards positive, forward and reverse.
Forward bias and reverse bias. If this is a PN junction, it is P, it is N. So how it is forward, how it is backward or reverse. P type should be connected to positive terminal or negative terminal, positive terminal or negative terminal. Just tell me. If I am having a battery, so how should I connect it? If you have a diode at your home, you have seen diode, I know, even you are using your devices that is made of diodes only. So how it is being forward biased?
For the P terminal connected to plus charge and N terminal connected to minus.
Yes, this is the forward bias. And for the reverse bias, just opposite, here negative and here positive. So this is the figure showing the forward bias and reverse biasing. So if we are connecting it in forward bias, here in this figure we can see, and in this figure it is reverse bias. Oh sorry, this is an equilibrium without biasing, and it is reverse bias and it is forward bias. So why do you think in the reverse bias there is no current flowing through this diode? Why it is blocking in the reverse bias? What is your understanding? What is your understanding? Why it is allowing current to flow in forward bias but not in reverse bias? Not in reverse bias but in forward bias. Okay, let's understood if you don't know. So this is a unbiased PN junction diode. If we are biasing it, this is the band gap. We can say NP type or PN type, that is same. So it is like NP type. So here what we are doing, it is unbiased. It is unbiased, and here if anything, or this is an N type and there are electrons, and these electrons if need to go here, so they have to cross this barrier, that is delta V, and they are not able to cross this barrier. So what happens in case of a forward bias, this delta V is decreased. Here you can see this is the delta V minus Vf, forward bias. So this is this barrier has been decreased by forward biasing. So this jumping of electron which was impossible before, now these electrons can jump easily. Now these electrons can jump easily here. But in case of a reverse bias, what happens? This barrier increases. Now delta V barrier is increased. How it is increasing? Like delta V plus Vf, or in case of this we can say reverse bias, VR. So this is the physical understanding on which we can say in forward bias conduction is taking place, but in case of reverse bias conduction is not allowing. Now let's move to the next thing, which is very basic one, that is the PN junction diode IV curve. Under dark, I am writing under dark because this course is about photovoltaics, and in case of photovoltaics we have a PN junction diode. These cells are those PV cells are nothing, just a PN junction diode under illuminated conditions or under light. So here I am not talking about those PV cells currently, that's why I am saying under dark condition. So give me like your view about this, how IV curve should look like. If I am drawing it like this and I am saying this is our voltage, negative V, and this is our I. Okay, what is the IV curve of a conductor? What is Ohm's law? So in case of conductor, we have Ohm's law. What Ohm's law say?
V is equal to IR.
Yes, V equals to IR. Actually, Ohm's law is saying here our current will be directly proportional to voltage, and R is a proportionality constant. So if it is constant, then it will be a straight line like this. This is our conductor. But in case of a diode, it is allowing some current to flow in forward, but it is non-linear. It is a non-linear. It is not linear in nature. And in the reverse bias, it is not allowing some current. It is not allowing. Ideally, it should be zero. But practically, there is some current which is known as reverse saturation current. So, this is the IV characteristics of a PN junction diode. This is the forward bias region and this is the reverse bias condition. Do you know what is this 0.7 volt? Above which it is behaving like a conductor.
Okay, sir.
What is this?
Okay, sir.
Okay. So this is that delta V which I was talking about. This is the barrier voltage. So now let's see some animations about all the things what we have studied till now. Let me open. I hope it is visible to you. Yes, no. See, this is the platform I was talking about. This is pveducation.org, and here in this part, just go to PN junction, and there are so many animations for everything. Like these are the table of content, and you can watch various animations. So in the PN junction, let's see first one, which is based on formation of PN junction. So this is our P-type semiconductor. This is our N-type semiconductor. Now this is an imaginary boundary. So we can say these are not PN junction. These are just P separately and N separately. And these are the hole and these are the electrons. Now we are making these PN junctions. So now you can see these electrons are going towards P type and these holes are coming towards the N type. Why? Because of difference in concentration. Because of difference in concentration. And at the same time, you can see if any electron or hole is coming in this depletion region, so it will move much faster. Why? Because of electric field. So inside this depletion region, drifting is being happening. You can say an electron or hole is drifting, and here it is diffusing. So let's see next. So it is saying when materials are joined, means we are making this PN junctions, carrier cross into the another region. These carriers are crossing one another region, and this is saying the same thing. The fixed ion cores that are left behind set up an electric field. It is saying the left one are creating this electric field, and this is the direction of field.
Sir, in back side, P side, minus charge is there. These are minority carriers. Minus charge is there and N type is starting their plus charge.
No, actually, these are not
This is
minority carriers. These are the dopant. These are the dopants.
Okay.
Like we are doping an N-type semiconductor or P-type semiconductor with some kind of impurity. So these are the impurities which has lose one electron,
Okay, sir.
and that's why they are positive in charge. So this is all about this depletion region or formation. Now let's move to the next one. So now this is an equilibrium condition. Equilibrium means we are not biasing this system. And now let's see the movement of those electrons and hole. See, this is the electron diffusion. This is an N-type semiconductor. There are more electrons, so they will diffuse towards this direction. These arrow are showing the direction of electrons. And this pink one, it is showing electron drift. I told you if any electron is there, it will be go back. See, just watch my cursor. If it is coming here, it will go back. See, it is coming back. Why? It is drifting here. From diffusion, they are coming to this depletion region, and in this depletion region, they are going back. And these are the four kind of movement: diffusion, electron diffusion in this direction, hole diffusion in this direction, electron drift this direction, and hole drift this direction towards the hole only. It is saying 0 voltage across diode, no current flow. So this is the equilibrium condition when diode is not under biasing. Now let's see what happens under biasing. See, this is a diode. We will bias it. See, first see in the equilibrium condition. This is the equilibrium condition. Same thing which we have seen the previous one. Now let's forward bias this. Now we have forwarded it. So in the forward bias, what is happening? These electrons are going from this N type to P type, and then they are completing this circuit and coming back. This is our forward bias. And here you can see in the forward bias, this electron diffusion is more and hole diffusion is more. So the thickness of the arrow is showing which is dominating. So here electron diffusion is dominating and hole diffusion is dominating. Now let's reverse bias this. So in case of a reverse bias, electron diffusion will be less and hole diffusion will be less. So we are suppressing the diffusion. See, there is a main important point. We are not changing the drift. Drift is automatic. It is not depending on the voltage. Here we are playing with the diffusion only. So in case of a forward bias, we are increasing the diffusion. In case of a reverse bias, we are decreasing the diffusion. So if we are decreasing the diffusion, so no current will flow. This is the diode equation. I think. Okay, so now they started with the PV. So this PV thing is coming in the next lecture. So before this, I'll stop this and I'll come to the lecture again. Yes. So now we will solve a few questions based on all these things we have studied. So let's see. First question says, and I want you to write in the chat box, your answer A, B, C or D. So which of the following is valid for PN junction diode in unbiased dark condition? It is saying for a PN junction diode, unbiased dark condition means equilibrium. And these are the options. So what happen in case of equilibrium? What was happening in this depletion region in this D? Okay. Suraj saying D, both generation and recombination take place in the depletion region. Okay. I am asking under equilibrium condition. So what is the source of generation?
Because
I totally understand if there is some generation, then the recombination will take place. But under equilibrium condition, why generation will take place? Others? Actually, in this condition, we have seen there was a depletion region and all the charges coming from diffusion only. There was no recombination or generation. See, what is the principle of solar cell? It's okay, Suraj. No, not to be sorry. We are learning here, and I'm just here to tell you what a solar cell do. In case of a solar cell, the generation take place inside the depletion region. But why? When light is illuminated on the surface of solar cell. But in case of a dark condition, there is no source of light or no source of generation. And if no generation, then no recombination. So answer is C. Neither generation nor recombination. Yes, Maladu, C. Okay, let's move to the next question, which says reverse saturation current. Reverse saturation current, which is I know, in a PN junction diode increases with, and these are the options. And I am telling you, it is a multiple selective question type, MSQ, so there may be answers more than one. It is just asking the reverse saturation current in a PN junction diode increases with. And I'll just tell you, if you have done some experiment in class 12th, there was an experiment in which we need to find the characteristics of different diode. And based on that, you can do this question easily. Say something with temperature or band gap. See, I'll tell you one thing, very simple. Just go with the band diagram. If it is a band diagram, and this is valence band, this is conduction band. If there should be some movement of charge carriers or just flow of current or any kind of current, so it is saying current. So when current can flow, either this decreases or number of charges increases. So this number of charges, does it increase with temperature? Why the conductivity of semiconductor increases with temperature?
Increases, sir.
Increases?
Yes, sir.
Yes. So this number of charge carriers increases with temperature, and this number of charge carriers increases the current. And if these are some minority charge carriers, then it will increase the reverse saturation current. Then first will be increase in temperature, and second, I told you this band gap is decreased, then conduction will increase. So it doesn't matter if it is minority charge carrier or majority charge carriers, it will constitute a current easily. It will be easy for a minority charge carrier to constitute a current in case of a decrease in band gap, and that's why C or D? C or D?
C, sir.
C. Increase in band gap. And one more way you can see, this is the equation where this minority charge carriers is represented by this, and here we have charge carriers density which depends on temperature. So directly we can say from this also. So what I told you, oh, decrease in band gap, sorry
Sir,
yes, decrease in band gap, I was told.
E, sir.
Yes,
Yes, sir. Yes, sir.
Yes, sir.
yeah.
Yes, sir.
So decrease in band gap will increase the current. So D is here, A and D. So let's move to the next question, which says the built-in potential. Built-in potential means?
VPI.
Yes, V. In a PN junction diode is dropped more. Dropped. And these are the options. Where it will be dropped. First, let me know, does it depend on concentration, doping concentration?
Yes, sir.
Oh,
Yes.
this is not a part of this. So, does it depend on the concentration? So, D is not the answer. And it is depending on the concentration. So, will it be high at high concentration? You just go with that width one, na? Width inversely proportional to this concentration or doping. PN junction diode built-in potential will drop. Where? High doping area or low doping area? Okay, let me ask you one question. If doping is more, width will be?
Increase.
If
The decrease, sir.
doping is more, then
will decrease.
electric field will, if more number of charge carriers are there, then the electric field will decrease or increase.
Increase, sir.
Increase.
Yes, sir.
So it is saying drop more. So it is drop means it is like decreasing. If ND directly proportional to E is directly proportional to V, and it is saying V is dropping, so ND should drop or increase? If
The
V
decrease.
decrease, so ND should be low or high? Low. Reason of low doping concentration.
Low.
So let's move next question, which one is very easy. When a reverse bias is applied to a PN junction diode, it will reverse bias. Just have seen the animations as well. And even from the second slide, we have seen it. Does this reverse bias will impact carrier concentration?
Sir, A.
A. Okay.
EVI plus with potential barrier.
Yes. It will raise the potential barrier for carrier transport. So we can easily say band gap does not depend on reverse bias. Concentration does not depend on reverse bias. So it will lower or raise, it will raise. Yes. And here you can see this is unbiased and this is reverse bias, so it is raising. So answer is A. Let's move to the next question, which says, which of the following is true for the depletion region width on heavily doping the N side in a PN junction diode? Just understand the question. It is saying if N side is highly doped, then what will happen regarding this depletion region width? And these are the options.
Sir, B.
Depletion region width decrease on N side.
B.
Sir, BD.
BD.
Yes.
Why D?
Sir, only BD, sir.
Only B. Yes. Only B. Why not D? Because
Doping नहीं हो रहा.
yes, doping is not happening in the P side, and this width is always divided into two half. This is like N side, this is P side, so it won't impact, but it will decrease. And this is the formula which says width is inversely proportional to concentration. So answer is B. Let's move to the next question, which says a silicon PV junction diode has an ideality factor of 1.5. The change in voltage when the current changes from 1 to 20 milliampere is. So you need to find out delta V when delta I is 20 milliampere. Oh, sorry, 19. It is 19 because it is increasing 1 to 20. So current is changing from 1 milliampere to 20 milliampere. So for the same thing, you need to find out the change in voltage. And these are the options. And if you need formula, then let me know. I am giving you some time to solve this question.
I equals to I0 e to the power EV by 18 as a formula
Yes,
n
yes.
minus 1.
Yeah. So this is the formula on your screen. You were saying right. This one is the formula. This is the ideal, not ideal. This is the diode equation. For starting this, I'll say you convert it into logarithmic equation.
So, 0.117.
0.117. You are saying this one is the answer.
Yes, sir.
Okay. You are okay. I got confused from this chat box. D. Yeah. Now you are right. D. What about others? Are they solving, or do I need to give you the solution? Very easy. You can do very simply. See, it is saying 1 milliampere. So just put 1 equals to I naught exponential Q V1 divided by NKT minus 1. And then write 20 equals to I naught E Q V2 divided by NKT minus 1. Just divide. So 20 equals to E Q VT upon NKT minus 1 divided by 1 and divided by E Q V 1 divided by NKT minus 1. Just cross multiplication and then solve it. Solve it for V1 minus V2. Oh, sorry, V2 minus V1. Or even V1 minus V2 will work. It will come in negative only. And this question is asking only the change. So change is always in positive term. Oh, Suraj also saying D. Okay then. D. Yes. This is the solution. Here you can see if you convert this equation in terms of delta V, then this is the short form of this equation. And in this equation, you directly can put these values. And yes, D is the answer here. Let's move to the next part, which says following is or are correct for depletion region in a PN junction diode. And these are the options. So there are few statements regarding the depletion region in a PN junction diode. You need to find out among these four which are correct or which are not correct or wrong. Maximum value of potential occurs at junction of the diode. Variation of electric field with position is linear. Ratio of depletion region with N and P side depends on the ratio of dopant concentration. Charge density gradient is proportional to the electric field. B and C. You are saying B and C. Variation of electric field with position is linear. Yes, true. Ratio of depletion region with N and P side depends on ratio of dopant concentration. Yes. And maximum value of potential occur at the junction.
A is false.
What you are saying? Can you write it in the chat box?
A false. A is not correct.
A false.
A is false.
B and C are right.
It is a linear curve.
Yes.
Electric field.
Yes. Wait a minute. Yes. Yes, B and C are the right answer here. So let's move to the next question, which may be last. I don't know. Let me check. The reverse saturation current in a PN junction diode does not depend on. No, this is not last. The reverse saturation current I naught in a PN junction diode does not depend on. These are the options. Just refer the diode IV characteristics here. A. Yes, Suraj, yes. Suraj saying A. Suraj saying A. What about others? See, career lifetime will depend, definitely will depend, because current is constituted with the carrier only, and if those carriers will die out soon, then the current will be, no more current will be there. Minority carrier concentration, definitely. If concentration is low, then reverse saturation current will be low, because this reverse saturation current is constituting of minority charge concentration. Diffusion length of charge carriers, this lifetime and diffusion charge carrier are the same thing.
Same.
It is
Yes,
just
option A.
it is just in terms of length, it does in terms of time. So, and here you can see this is the IV characteristics, and this is the reverse saturation current, and this is a range of voltage. So it is not depending on applied bias. So yes, this is A. Yes, so that's right. Let's move to the next and last question, which says, for an ideal diode, ideality factor is, and these are the options, which is very simple question, but you need to tell me one more thing. What do you understand by this ideality factor? Suraj saying B, 1.5. I think you are referring the questions which was in this slide only. Ideality factor of ideal diode. Ideality factor of ideal diode. One. Suraj saying 1. Okay, Malade is also saying 1. So I'm saying 1 is the answer. Okay, you are right. 1 is the answer. So do you understand what is this ideality factor is? Okay, how do we find this ideality factor? From theory? See, to find a value of anything, any component in the electrical things, there are two ways. One is experimental way, like curve fitting and all, and second one is from theory, like starting from the scratch, from the concentration, then voltage and all those things. So there are two ways by which we can carry out the value of anything. So in case of an ideality factor, how do we calculate this value? So do we calculate it using theory part or from this curve fitting part? You don't know about this, okay. So I just want to tell you one thing. This ideality factor is just an approximate value which is kind of curve fitting. Ideally, a diode should behave like this. Here it should be 0 current and it should increase here. So this part should be 0 here. But it is not 0, it is like this. And here also it should be like this or some non-linear, but there should be no new voltage as well. So this curve fitting factor is ideality factor. It shows how much far it is from an ideal diode. And in this curve equation, I equals to I naught exponential QV and KT minus 1. This N, it represents this ideality factor, and I'm telling you or I'm giving you a homework which is very interesting. Just do you have, what do you do? Do you have, use Python, MATLAB or Excel?
Excel.
Excel only.
MATLAB, sir.
MATLAB okay. So any platform, if you are using MATLAB or Excel or Python, I just want you to take this, put different value of voltage and like make it constant. K and T are always constant. Take T as 298 Kelvin and K just KB, Boltzmann constant 1.3 something like this. And Q you already know, charge of electron. And this I naught you can take any constant from the literature only, or here I can say take it 10 raised to power minus 6. And do one thing, plot curves with different value of n. Just change the value of n from 1 to 5 with a difference of 0.2. So with a difference of 0.2, just change the value of this n, and then you will see the impact of this ideality factor clearly. Is it okay? Will you do it? Yes, do it. And even if you finding any curve, you can, how will you give it to me? So you can mail me. I'm just writing a mail ID here. ravik@iitb.ac.in. So you just mail here what all curves you are getting. Is it fine? Okay. So we are done with this class, and I am going to upload this lecture on YouTube, and all other lectures are there already. I have seen there are few new students, so they may not know about this YouTube channel. So I am just giving them the link again, and they can watch the previous lecture as well. And this lecture I also upload on the YouTube in next 10 to 20 minutes. Is it fine? Yeah. So this is the channel which I put in the comment box, and this class as well as other 3 classes which I have taken already, you can watch those classes in the YouTube. And if you have any question from those classes, you can ask in the comment there. I'll reply there only. Or even if you have questions, you can come in the next class, or you can write to me on my email ID. Or also you have an like platform there, discussion forum, you can write there as well. Is it fine? Okay. So if you have any doubt, any question or anything to ask, you can ask. Or if you haven't watched this class, or if you joined late, you can watch this class on the YouTube channel and other class as well. And otherwise you can leave and you can. So there are some new students which are coming. So we have completed this class, and I am going to upload this class. Why people are joining very late? Okay, it's fine. So for the latecomers, I am telling you, so we are done with this class. So for the latecomers, I am telling we are done with this class, and there are other 3 classes as well which are being uploaded or have been uploaded on the YouTube channel. And this class I will upload in the next 10 to 20 minutes, and you can watch this there. And if you have any doubt, you can ask in the comment as well. And this channel YouTube link Our YouTube channel link is in the chat box. You can check it. Any question you can ask. If not, if you wish to leave, you can leave. I am here for the next 5 to 10 minutes. If you want to ask anything, you can ask. Thank you, Suraj. Be responsive as you are, so you will learn more. I am going to end this class in next 5 to 10 minutes. If you have any question, any doubt, anything related to this class or anything from this subject, you can ask.